Hey you guys, if you saw how I was recording this, you'd be laughing because it's pretty funny. I've got this resting on like this old crusty chair. Anyway, I'm going to go through a couple of these exam questions with you. First of all, 3C. In order to do 3C, we kind of have to know 3B. So I'll work that out for you now. So we've got, after a period of time, solid copper had formed and it was removed. The dried mass had 0.395 grams. And that was just the deposit. And so what we're first going to do is work out the number of moles of copper. So that's our moles of copper. Now, to work out the number of moles of nickel, remember the nickel in this question is the anode, and so the nickel's getting oxidized, so it's going to get less. The mass of nickel that reacts can be worked out from the moles. In the overall cell reaction, which you all got, nickel plus copper 2 plus turns into copper plus nickel 2 plus. So if I know the mass of copper, I can work the moles out. Once I know the moles, I can see the moles of the nickel is the same, and then I can convert back to a mass. So the number of moles of nickel equals 0.00602, and therefore mass of nickel equals 0.00602. I don't have a data book on me. Let me just look it up on my computer, bear with me. Nickel 58.7, so we times that by 58.7. .365 grams. Now to work out the final mass of the electrode would go 10.27, which was its initial mass from up here, there, and take away 0.365, and we get 9.90 grams, 3 sig figs. Right, now to do the second part of this one, calculate the final concentration of the nickel, what we've got to remember is there was some nickel solution there to start with, nickel nitrate. Isn't it interesting that they've got the cell backwards? Luckily they fixed that. So we've got 200 mils of 1 mole of nickel nitrate solution. 200 mils, sorry, not 200 moles. So the initial number of moles in here, number of moles, nickel 2 plus initial equals C times V. So we've got 1 times 200 times 10 to the negative 3 equals 0.2 mole. Okay. Then we've got to work out what number of moles of nickel reacts. Number of moles nickel 2 plus reacting equals, we had it up here, 0.00602 moles. Because to find the final concentration, it's going to be C equals N over V. V is the total volume of the solution, but the N will be the amount of moles of nickel that's in the solution. So remember, we've got to take the initial moles and we're going to have to add the moles that gets oxidized from the nickel anode. So it's going to be 0.2 plus 0.006. So we get that, and then divide that by the volume of the solution, which was 200 mils, and we get 1.03 moles per litre. So the concentration of nickel in this solution's increased because, let's pretend that's nickel, because the nickel electrode has been oxidized, it's broken down, so it's adding more nickel 2 plus into the solution. So if you want a good way of remembering this, number of moles initial equals number of moles reacted plus number of moles excess, or usually this is the way that you work it out. Number of moles excess equals number of moles initial, take number of moles reacted. Okay, the next one I wanted to talk about was 4C. Not many of you got this one. So there's two different ways you could have done this. I think most people got, oh, hang on, I'll talk about 4A first. 4A was, I think you all got the cathode reaction. It was oxygen. You just grabbed the one that had H plus from the data book. So this forms two CO2s, and then you use COs to balance it. So carbon's already balanced, 3 waters to balance the oxygens, and then we've got to add 6, and 6 is 12 hydrogens and 12 electrons. And then put your states in. What we can see is 1 mole of ethanol produces 12 moles of electrons. So a lot of you didn't do this part right, because when you worked out the moles of ethanol, you had to times that by 12 to get the number of moles of electrons. So to do this last one, to work out the energy, the voltage is definitely related. There's two different ways you could use this. You could either go E equals Q times V, Q being the charge. Now, how could we work out the charge on 1 mole of ethanol? Well, the number of moles of electrons, Q equals number of moles of electrons times Faraday's constant. So if we had 1 mole of ethanol, that would be 12 moles of electrons according to the equation we had before. Times that by 96,500, and that will give us an amount of charge. Times that by the voltage, so it's going to be 12 times 96,500 times 1.1. That will give us an answer in joules. And then we've just got to convert that into kilojoules, and that will be our answer. Let's just do it for fun. So that's in joules, divide by 1,000, give us in kilojoules. Put in the right amount of sig figs, so it'll be 1.27 times 10 to the 3 kilojoules per mole. If you can hear me struggling to breathe, it's because I'm kind of leaning over this stupid old crusty chair trying to record this video because my phone's resting on it. Okay, the next one I wanted to do was 5A. So we've got methanol can be used as a fuel. The reaction for the production is this. The following changes are made to a gaseous mixture of those 3 things. At 300, consider the effect on the masses at blah, blah, blah. Write the words increase, decrease, or no change. Okay, a lot of you got most of it right, but didn't get this one right, so I wanted to talk about that. More CO is added at a constant volume. What does that do to the mass of CO? So if we add some of this in, a Ford reaction happens to partially consume it. But remember, it doesn't actually consume all of it. So if we had, let's just say we had 5 grams at equilibrium, and then we added in another 5 grams, it's never going to get back to 5 grams or less. After equilibrium is re-established, it might be 6 grams or 8 grams or something like that. And if you want to look at it in your concentration time graph, it would look something like this. There's our CO. We add some CO and it comes back down, but the mass of it is overall still higher than it was to start with. What else did I have? 5A, 7AB. Okay. Most of you got this one, so that was butanoic acid. The chemical test for carboxyl groups, because this was CH3, CH2, CH2, COOH. The chemical test is to add some kind of carbonate and look for bubbles. If bubbles are produced, you know that you've got an acidic group on your molecule. This one, you all figured out that an ester was produced and it was methyl butanoate, and you could draw its semi-structural formula. The thing that you struggled with was the chemical test. There isn't actually a chemical test that we've learnt about, but the test that the answers said you can either smell it and see if it smells sweet, or esters are not soluble in water, and so they should form an insoluble layer which is less dense, so it'll float on top of the aqueous layer. So you could look for the presence of a layer on top of your reaction mixture. Question 8 was the one that you really nailed. That was that one for anyone that wanted to know. Really, really well done. Question 9C I had down. A lot of you struggled with this one. So we've got 1 tonne of vegetable oil. So this is the thing from the previous page. And it says it requires 4.9 kilograms of hydrogen to hydrogenate the triglyceride. So let's just understand what's going on first. This triglyceride is an oil. When they turn it into margarine, what they do is they add hydrogen to it, and the hydrogen reacts across the double bond in the carbons, making it saturated, and then once it's saturated it has a higher melting point, and so it's more likely to be found as a solid at room temperature. So what we're talking about is getting rid of these 4 double bonds by adding hydrogen. So we can see that one of these would require 4 hydrogens to be hydrogenated. What the next part of the question is saying though, is that when they do it, they don't actually react all of them, just most of them. And so we have to work out what the ratio is between the vegetable oil, the triglyceride, and the hydrogen. So we work out the moles of the vegetable oil first. Number of moles is mass over molar mass. 1 tonne is 10 to the 6 grams. VCAR will usually tell you that. And the molar mass we can see from the previous page is 882. And so we get 10 to the 6 over, Mr. Leslie, 1133.78. Number of moles of hydrogen equals mass over molar mass, 4.9 kilos. Convert that to grams, of course, divided by 2. Shouldn't have to do this in the calculator, should I? 2450 moles. Okay, so we can see now with this many moles of triglyceride reacted with this many moles of hydrogen. If it had fully reacted, this answer here should be 4 times this number, but it's obviously less. So they're saying what's the average amount that reacts per triglyceride? The way that you could work this out is to find the simplest ratio between the two of these. And so that would be dividing both of these by the smallest number. And we get 2.16, and that's obviously 1. So what this is telling us is for every 1 triglyceride, on average 2.16 of the double bonds have been hydrogenated, so they've been turned into single carbon-carbon bonds. To do this next part of the question, you grab that 2.16, you divide it over the 4, which is the possible, times by 100, and you get your total percent. That gives us 54% of the double bonds had been hydrogenated. So that was 9C. Let's do 10B. I think this question was fairly poorly written, and I also think that you guys didn't necessarily read the question properly or understand it. Most of you got this bit right for the number of different environments in each of the molecules. So it was 6, 3, 3, 2, 3, 5, 5. So that's just the number of different hydrogen environments. To do the second part, you could do that by drawing it out or just recognizing the structure. The second part is saying that 3 of these are compounds X, Y, or Z. We've got to work out which ones they are. So compound X, we're looking for 3 signals. So it's either that one, or that one. No splitting of the peaks. So if we've got no splitting of the peaks, they all have to be separated from each other. And in this structure here, we can see that they're all separated. If you draw this out, you'll see those aren't split because there's no hydrogens on that carbon. These aren't split because there's no hydrogens next door. These aren't split because there's no carbon with hydrogens next to it. So that one's X. Y has a triplet, quartet, and singlet. So Y is this one because we've got triplet, quartet here, and that's a singlet there. Now Z is a bugger because there's nothing there that makes 12 peaks. 12 would mean it has to have 11 hydrogens next to it, which none of them do. But the closest one there is that one. Right, what else did I have written down? First 2 parts of 11. Probably the most poorly done on the whole exam, so maybe that's my fault. When you're drawing optical isomers, that means that they're chiral, and there's 2 different ways you can do that. The first way is that you can draw it with a mirror plane. Whenever you draw optical isomers, you have to draw the dots and the what's it called, the bold bonds. So I'll show you what that means. So if we draw our C4H10O, we can see that the bromine's on the second carbon, so we know the hydroxyl group's going to be on the second carbon after the reaction. So I'm just going to draw it without the hydrogen so you can see the difference. So if I draw a bold bond and a dashed bond, so remember the bold bonds means it's coming out of the page towards you, and the dashed bond means it's going into the page. So there's one isomer. To draw the other one, I draw exactly the opposite of that, i.e. the mirror image. Forgot to put my hydrogens on there. So draw exactly the opposite, and that will be the other enantiomer. So there's a pair there. So that's one way you can do it. The other way you can do it, I'll show you both. Oh, my phone's heating up. I'll just do it with a smaller molecule so you can see. So ClH. Let's just say we've got this molecule, Br and I. If I want to draw the other isomer of that without doing the mirror image, what you do is you draw everything the same, except you swap the two things that were on the dotted and the dashed. So that would now be Br and I. So you've got two different ways of drawing pairs of optical isomers. When you're explaining the relationship, you say that these are optical isomers, meaning that they're non-superimposable mirror images of each other. Non-superimposable mirror image.